right, so hello everyone. This is the schematic of our project, and we are going to use this system to analyze and perform our computational model and like all the calculations. Right, so here we go. So this is actually a book problem. So in which we have given the mass of the wheel, mass of the motorcycle, the moment, wheel of moment, the moment of inertia of the wheel, and the radius. And we have three output variables, which are acceleration, pin reaction forces, and braking distance. Right, so here we go with our derivations. So first, we created 3-by diagrams for front wheel, rear wheel, and whole system of the bike and the person. And after getting done with our 3-by diagram, we move forward to create system of equations. By the way, first we use our kinematics to derive the relationship between velocity and acceleration. Then we got 3 equations for rear wheel, 3 equations for the front wheel, and 3 for the motorcycle. And 1 is acceleration, which is equal to radius times the angular acceleration. So total 10 equations. And we plug in, we plug this 10 equation into a matrix, and we derive from there, we derive acceleration in x direction and 2 normal forces. All right, after doing that, we have gone, we move forward to do our work energy analysis. And from that, we set up the expression for the braking distance. And I'll now move forward. I'll now hand it over to Usman for computational model.
So hi, so for our experiment, we created a model using Python, and here is a code. So just a brief overview of it is, here's a matrix we set up for the derived equations, and what we do, we loop increasing change by changing the mass, and we basically do it for several of the output variables to see what we get. So I'm gonna run the code right now. When you click run, you click run. So it's adding us some mass. So we'll just use 142. You can choose how much you want, and as you experiment, you can see that in all of those 10 other variables, there was auto computed values. And here's a graph of the accelerations, another graph of the acceleration versus mass, of the rear pin, front pin, and then the braking distance, and velocity versus time. And lastly, it's the angular velocity versus time. And that's it. So, and as you can see, we compared our values with the theoretical and computational model, and this model almost is 100%. It's relatively accurate by approximately 6 decimal digits, what is accurate in engineering. Now I'll hand it over to Danish to for the conclusion.
Thank you, Usman. Based on our results, we found out that increasing the velocity of the bike results in a higher braking distance based on the upward trend of the graph over here. And when the mass of the system increases, the amount of force exerted on the pin support also increases based on the upward trend of the graph of this part and this part. And lastly, the acceleration of the system is inversely proportional to the mass, as when the mass of the body increases, the acceleration of the body decreases. And yeah, that's it.